Today's notes, 64 and 65. Probability of dependent events and practice. Okay, so in our previous lesson, we had the probability of independent events, meaning that the two things or three things or however many things we wanted were not going to affect each other, right? If you did one thing, flipping a coin, and then you picked a letter from the alphabet, those are two dependent events. So the events do not affect each other. And so dependent events will affect each other. It depends on what happens first or what you do first. So the outcome, and remember we talked about the number of outcomes was how many choices there were. So how many choices, which is our denominator. The outcome affects the other outcomes. So our denominator is going to change. So if we remember that the outcome is the denominator, it's the total number of choices, that outcome is going to change. So for example, if we said you have 5 blue marbles, 4 red marbles, and let's go 10 green marbles. Probability, independent probability, which is what we did yesterday. The outcome is 20. So a problem that would talk about independent probability, that's our story problem, just so that we can keep track of it. Independent probability would be the probability of a blue. Right? I have 5 blues out of 5 plus 4 is 9, plus 10 is 19. And I'm done. That's it. If I said the probability, oops, that's a P, probability of blue or red, well, blue plus red, that's 9 out of 19. Dependent probability switches it up a little bit. Dependent probability the outcome, the first outcome is 20. and every other outcome changes. Other outcomes change. So a problem would say things like this. An example of dependent probability would be, what is the probability of a blue? Then, without replacing the marble, the probability of a green. And that, the key part, the big part of this dependent is without replacing. So what happens is, I say, okay, the probability of a blue is still 5 out of, oh, I said 20. It's not 20, it's 19. I said 20 up here too. Oh my gosh. Guys, it's not 20, it's 19. I think in my head I wanted it to be 20, but I didn't make it work. Probability is 19. Outcome is 19. So it's 5 out of 19. 5 out of 19 is blue. But then the probability of a green next, but I didn't replace it. Well, now there are 10 greens, but now there are only, instead of 19 marbles, I took one out, there are 18 marbles, which is going to simplify. And remember, if you can't, 5/19 isn't going to simplify. If you can simplify, you want to simplify. So this is 5/9. My outcomes, my number of outcomes changed. So the probability is 5/19 times 5/9, which is 19 times 9, 25 over 171. And that does not simplify. So dependent probability really can change this outcome, right? It really does change the way that we do our fractions that represent our chance, what we want, over the total number of outcomes. If I was to say blue, then green, and then red, all without replacing, I would have 19 as my first outcome, then 18, and then my next outcome would be 17. So dependent probability is when your number of outcomes is going to constantly be changing. So let's do the probability of a vowel, then a consonant, without replacing. So let's assume that this is all of the letters of the alphabet. So a vowel, probability of a vowel, A, E, I, O, U, 5 out of 26 letters in the alphabet. That does not simplify. And then the probability of a consonant, well, 26 minus 5, if there are 5 vowels, that means that there are 21 consonants. But my denominator is going to change because it's without replacement, which is 25. So my overall probability of this event happening is 5/26 times 21 over 25. I can simplify. 1 times 21 is 21 over 26 times 5 is 130. And again, I had 26 because I started with 26 letters of the alphabet. I picked one. Now there are only 25 to choose from and 21 options. Now, the other part of this is that you assume when you're finding that theoretical probability, you're assuming that this first thing is happening so you can continue on to the next. Right? Experimental probability is different. If I picked the first time and I didn't get a vowel, because I don't have a very good chance of getting a vowel, my experimental probability is going to be 0. But that's because it's an experiment. This is the mathematical chances of this happening. If I did this experiment 130 times, I could expect a vowel then a consonant to happen 21 times out of 130 experiments. If I did probability of let's go red card, then a face card without replacing. I'm going to find the probability of a red card. So the probability of a red, well, in a deck of cards, I know that there are 52 cards and half, right? Half of them. Or I could just say half. I don't even have to do 52 cards divided by 2. I don't have to do 26 over 52. I can just know that half of the cards are red. I do need to know that there were 52 cards to begin with, because now the probability of a face card, there are 3 face cards, but there are 4 types of each. So that's 12 out of 51, because I changed from 52 cards to 51 cards. So my overall probability is 1/2 times 12 over 51, which is 6/51. Right, I used my cross product or my cross to simplify. Both are even, divide by 2. Let's do another one with just cards. Probability of a red card. Let's do then a black card without replacement. Now, if I did put it back, right? If I put back my card, I picked one, put it back, then picked again, that would be 1/2 and 1/2. However, it's not, because probability of a red card, again, is 1 out of 2. But this time the probability of a black card is not 1 out of 2. It's 26 choices out of 51. It's not 26 out of 52 anymore. It's 26 out of 51 because I picked a card and kept it. So 1/2 times 26 over 51. That's 1, that's 13, is 13 out of 51. So dependent probability, the number of outcomes is going to change after the first event. After the first thing you find, your denominator, your number of outcomes is decreasing because you are not replacing it. independent probability, the outcomes stay the same. But dependent probability, the second, third, fourth, whatever, changes depending on the first one.